Um, my talk will be about JavaScript variables. So we'll cover in depth how they work. And there's some tricky things. And if you understand what's going on behind the scenes, then it helps you with understanding the language better and you can work with it better. How many of you have heard the word closure already? All right, very good. So after the talk, you will actually know what it is, should you not already know. So let's start with a few definitions. The scope of a variable. That means where the variable is accessible. So here you have an example. You have the variable x, and the scope of that variable is the function foo. Or you could also say the direct scope of x. Then there are two adjectives, static and dynamic. You've probably heard these words before, but they have a specific meaning when it comes to programming languages that is universal. Static means something that retains the source code. So whenever a phenomenon is static, you can simply look at the source code and determine what is going on. So in this example, again, there's a variable, and the scope of a variable is a static property. So you can, just by looking at the source code, you can determine the scope of x. So whatever is in here, whatever happens outside, it doesn't change the fact that x is accessible within the curly braces in here. So scope is something static. And the opposite kind of static is dynamic. And that means at runtime. So if a feature is dynamic, you have to run the program in order to find out what's going on. And roughly, function calls are a dynamic feature. You have to run the program, and here, f calling g, that is something dynamic. And var declarations in JavaScript, that's kind of a weird thing, are function scope. In other programming languages, what you have is block scoping. So here you have a block, and you have a variable in there, and in block scope languages, foo would never leave the block. So you wouldn't be, in say Java, you wouldn't be able to access foo down here. And that's kind of the normal thing to do, that you are block scoped. JavaScript, in contrast, is function scope, which means that if you have, say, a for loop or any kind of block inside, then foo is always accessible within the complete function, which is why you can access it down here. Thankfully, ECMAScript 6 will bring us block scoping. So there will be a new way for declaring variables via let, and that will enable block scoping. And kind of the slogan is, let is the new bar. An additional feature that's really common in programming languages is the ability to nest scopes. And JavaScript is really good at that. Here's an example. You have two scopes. On one hand, you have the scope of foo, and on the other hand, you have the scope of bar. And the scope of bar is nested inside the scope of foo. And Christy. So bar is nested inside of foo. That is nesting, and that is a static feature. And what that means is that everything that is accessible in an outer scope is also accessible in all inner scopes. So if you have a parameter up here or a variable and it's accessible in foo, it will also be accessible in bar. Environments. Environments are about managing variables. So if you think about how to implement variables, that's kind of the under the hood management that is going on. And it doesn't necessarily mean that that's how engines implement it, but that is how it's specified in the ECMAScript specification. So you have the specification has to kind of find a way to express things so that they are easy to understand, and the specification dictates to implementers of engines how they should implement it. And the ECMAScript specification uses environments to tell everybody this is how variables are supposed to work. And environments are simply a data structure for storing variables, storage space for variables. They are maps from variable names to values. So they are, in many ways, quite similar to objects in JavaScript. But it's an internal data structure, so it's at the level of the JavaScript engine. You can't access environments in the language itself. It's how JavaScript is implemented. And there are two features that environments must support. One is you need fresh variables every time a function is called. So if you have a function f and you call it, and it has a parameter, every time you call it, you need fresh variables, fresh storage, and new variables. Otherwise, recursion doesn't work. And you have nested scoping. And then you are in an inner scope. You don't want to lose your connection to data in the outer scope. So let's look at examples. So this is a function, a faculty function that uses recursion to compute the result. And as long as the parameter, or as soon as the parameter is less than or equal to 1, you can return 1 and you're done. Otherwise, you multiply n by a recursive call with n minus 1. And then you go down. You start at a high number, you go down, and use recursion. And every time FAC calls itself, you need fresh storage for n. And somehow, environments have to be able to do that, have to implement that correctly. And the common data structure for doing so is a stack. Because you call the function, and every time you have a function call, you have more storage, more storage, more storage, and then you leave the function and then you reclaim it and you go back down. So it's a typical stack scenario. Recursive call, you call yourself, you call yourself, you call yourself, then you leave, and then you reclaim the storage. So what the ECMAScript specification says is that if you are a JavaScript engine, in order to manage the environments, you will have a stack of so-called execution contexts, and these are simply pointers to environments. And that is still now a bit difficult to understand, very abstract, but we'll look at an example now. Okay, I'll continue. Right. Otherwise, you can always look at these if your neck kind of doesn't. Let's look at what happens actually. Let's look at what environments actually are and how they work. And this is the function fac that we just have seen, and this is the stack. So as more recursive function calls happen, this stack will grow, and it has a pointer to an environment. And at the beginning, we are here, and we are in the global scope. So what you see here, this is the, so this is the environment for global variables. And you can see foo is a global variable. It's stored down here. It has the value ABC. Fac is a global variable, and its value is a function. So this is the stack of environments at the very beginning of the program, and you can see that this is where the global variables are stored. Next step. Now we are actually making a function call. And what that means is you need fresh storage for the parameters and the local variables. And you push an environment onto the stack. And the environment has storage space for the parameter n. And n is initially 2, because you've just made a function call and the parameter was 2. So the stack size increases. And then, because we're not yet done, because n is not less than or equal to 1, we continue, we make another function call. And that means that we add yet another environment to the stack. And this time, because you call, fac calls itself with n minus 1, it calls itself with 1, which is why the new value of n now is 1. And then we're actually done. Fac returns, and what happens then is you pop the environment, then this one is done as well, you pop it again, and you're back in global scope. So this is the kind of where the stack grows and then shrinks again. And you can see that the global variables, because you never, unless you leave the program, you never kind of leave the global space. So global variables are always there. And then there's a second dimension, and that's about nesting scopes. And this is an example where nesting happens. G is nested inside F, and how that is implemented is every environment points to its surrounding environment. So when you call G eventually, the environment of G will have a field outer, and that will point to the environment of F. And if you are in G and you want to find like a value for a variable, and you want to find out what is the value of X, you first look in the environment of G, and then you continue to the outer environment and you search there, and then you find the value for X. And that is how nested scopes happen. Because all that you need to do is, if you can't find a variable in G, you continue your search in F. And that's how the nesting is implemented. And the field outer is initialized via a property scope in the function. And so, because each function records where it was created. And G records I created inside F, and that value can then be used to properly initialize the field outer. And again, this is a bit abstract now. It will become clearer once we look at an example. So this is the function at the beginning. Again, we are here, and we are in a global scope. In global scope, only a single variable exists, and that is f. And the value of f is a function. So that's all that's there at the beginning. It's distracting, I'm sorry. And the next step, so this is where we are initially. These are the global variables. Then next what we do is we make a function call. And again, we have this stack-like thing. You need new storage for the parameter x. You need new storage for foo, which is a local variable. And you need new storage for g. So in order to implement the function call for f, we need all that storage space that is there. And now we can actually handle nesting properly. Because now we have a pointer from the environment of f to the global variables. And that means that if you are in f and you're actually trying to access f, you will find it. You will start your search down here, you look for f, you don't find it, and then you continue to the outer environment, and that's where you find it. So this is how you, even once you're inside a function, you're still connected to the global scope, to the global variables, because every scope is always nested within the global scope. And then the next step is, once you're inside f, you may get another function call. You call g with two parameters, 7 and 1. And you push another environment on the stack. Now you need storage space for y and z, and for bar. And, well, these are the parameter values. Bar is undefined because we haven't assigned anything. And again, the environment of G points via outer to the environment of F. And that is why, while you are in G, you can still access foo up here, and you can still access F. And the way to initialize outer is because G has and records via the scope where it was created, where it was born. And yeah, I think later there will be a better example for the initialization of outer. So closures. Now we have all the ingredients in order to implement closures. And let's think a moment, would you be able to define what a closure is? And that is because people talk about closures, but what the F does that actually mean? What's a closure? And people use it liberally, and it actually has a fairly simple definition, but it's nice to first see it in action and to kind of see what closures do for us, why they are useful. And this is a common pattern that JavaScript enables that functional programming languages do a lot. So Scheme is really good at this kind of thing. And Scheme, which is a Lisp-like programming language, is what was copied by JavaScript. So JavaScript is very powerful with regard to environments, variables, and closures because it borrowed that stuff from Scheme. And yeah, that's a programming language you should check out. It's a really nice one. So what create_inc does, you call it with a value. Well, you can see it down here. and it's up here, yeah, up here. And what it does, it returns a function. And that function has start value as kind of a hidden global variable inside. So the function that create ink returns here that we store in ink, you can call it several times, and each time it returns something different because it remembers start value up here, because it's nested inside create ink. It still has a connection, and it can use it as if start value was a global variable. So you call create ink, it returns a function, you assign the function to ink, and then I'm really sorry. And then you call it once, it returns the initial value plus 1, then you call it a second time, and it returns the initial value plus, it returns 6 plus 2. Is that clear? Does everybody understand what's going on? If not, please ask. Feel free, it's important that you understand that one. It should be fairly simple. So what is a closure? A closure is actually just a function plus the connection to its birth scope that a function has. So the reason why this inner function can still access start value even once it has left create ink is because it stays connected to its birthplace. And this connection is important. And this connection happens, as I mentioned before, via the internal property scope that all functions have. So that's something you can't access via JavaScript, but that is used by JavaScript engines, at least conceptually. And again, an example will help. So if we are here at the very beginning, then this is the global environment once again. And this is the stack. So we're still in the global scope. And now ink is still undefined. And create ink points to a function, which is an object. And the function object has a property that is called scope. And it points to its birth scope. So what we're saying here is that create ink was created in global scope. It points back to the environment that was active when create ink was born. And the next step is we call create ink. And again, we allocate new storage space for this invocation, and all we need at the beginning is storage space for start value, and that has the value 5. So that's the usual function call stack thing. And we can see that because scope points to the global environment, outer now points to the global environment too, which is exactly what we want. Because down here, this is the environment of create ink, right? And it's nested inside the global environment, which is up here. So we will be able to, from down here, we will be able to access all global variables. And the next step, once we return, we find that, and it's very interesting to look at what changes now, because the what has actually happened. So this was active while we called create inc, and once we're done with that, it's gone. So the stack is smaller. But because now there's a function in inc, and what's inside inc is the function that has been returned by create inc. And that function keeps the environment alive, because the function we return here, the scope of that function is create inc. Oh my goodness. So inc now holds the function that we've returned, and the birth scope of that function is the scope of create inc, which is why inc points to that environment. And this reference prevents the environment from create inc from becoming garbage collected. Any questions so far? All right, it may make sense that you may have to go through it afterwards again, but it's like the basic mechanisms are simple. It's like the stack and the outer, but you may have to look at it to figure out like what exactly goes on like later again. So this is what's important to note is that the environment of create inc stays around. It isn't garbage collected because inc refers to it, points to it. Okay, next step. Now we call inc up here, and again we have the stack. Something new is pushed onto the stack, and we call inc with which is up, the actual function is up here. We call it with the parameter 1, which means that a new environment is created for this function up here, and the value of step is 1. And again, outer works as we expected, because this is the environment of the function in here, of this one, and start value, this environment here, is the environment of create inc. So it's correct because this function is nested inside create inc, and create inc is nested inside the global environment. So the chain of outer environments perfectly reflects the nesting that goes on in the scope, in the code. So it really maps the static form or shape of the program. And this means that inc is currently active. Once it leaves, we have no need, so this can be removed. We don't need it anymore, but start value stays all the time, which is why we always have the current value in here, while we remember the past by a start value. And now we're back back from this function call. We're back in the stack is small again. The global scope is active, and we're almost back where we were at the beginning, but start value has changed. So, how much do we have more time? All right, basically out of time. One more phenomenon is, or not. There is, if you look at this function here, this code does not work as expected. So what we have is, we have an empty array. We start a for loop and count from 0 to 3. And then we create a new function, and we push it onto the array. So what we have is an array of functions, and we would expect the function at index 0 to return 0, the function at index 1 to return 1, the function at index 3, at index 2 to return 2, right? Yeah, and and that's what we do here. We call one of the we create an array and we call the function at index 1, and the and it doesn't return 1, it returns 3. And why is that? Yes, because due to a closure, each function has a live connection. It doesn't lose the connection to I. And after the loop is done, the value of I is 3, because we've counted up. So once the loop is over, the value of I is 3, and each function returns I, and it returns the current value, not the value that I had when the function was created. So each of the functions in the array returns 3, and not, well, and not kind of their index. And the way you do that is, who has used an iffy before? This kind of self-invoked function. A function that calls itself. All right, so this is kind of like kind of advanced, but roughly, and you can actually there's a lot of nice explanations on the web and also online in the online version of my book, which is free. What you do here, you wrap a function around it to actually create a new environment for each function. So each function, oh my goodness. So each function creates, gets a fresh environment, and in that environment, you put the current value of I. So you create a fresh environment for func, and you put I into pause, and this is a copy for this one loop iteration. So each function has its own environment and gets like its own copy for itself, its own copy. And sharing doesn't occur, and that's what we want actually. So if you want to look up what an iffy is, you can go to speakingjazz.com. My complete book is, you can read it for free online, and it explains what ifs are good for and why they're useful.
5 minutes for questions.
All right.
Hello, I want to ask a question about the last example. Could this problem be solved with help of let?
Could it be solved how?
You use function. Please next slide.
Yeah.
As I understood, you use function scope only for scoping variable post to be unique for every function. Is it right? And in the beginning of the presentation, you said that in the ECMAScript 6, there is another way of declaring variables. Let.
Very good, excellent question.
Maybe it's used here.
Yeah, it doesn't work here because what you have, this is not about block scoping. Or no, you're totally right. I'm sorry, my bad. Absolutely. What you would do is you wouldn't have to do this kind of weird ass thing with a function that calls itself. You could simply use curly braces. So you could achieve the same effect by just open a curly brace, close a curly brace, and that's it. And that would automatically create a new scope for let, precisely the literal. Additionally, though, in ECMAScript 6, if you use the for loop, it creates a new environment for every loop invocation. So the loop variable is never shared, You always get, so that prevents that kind of a mistake, which is, and this kind of a mistake, it doesn't happen very often, but when it happens, it's really hard to debug. And even really experienced programmers get this wrong. So, which is why it'll be nice in ECMAScript 6 that in practice you can't have that.
Thank you.
Oh, my previous slide.
Sure. This one? No. This one? No. This one? Further? More? Do you have the number of the slide? Further? Still?
This wrong answer.
What?
Well, answer пускай переводит. Ответ функции, где дает 3.
Alright. Oh. Okay, 29. 29. This one. Oh, this one. This one. Alright, I'm sorry, okay.
Не решит ли проблему, если передавать и как параметр, причем параметр тоже с именем и, тогда получится, что перекрываться будут области видимости одним и тем же именем.
Yeah, me too. Can somebody translate?
So you can ask this question on during the pause.
During the break. Yeah. Or you can translate it. Is it something simple? Okay. What
If we put I as parameter?
Oh yes, absolutely. Yeah, that's yeah, absolutely. Yeah, it's a very nice way of doing it. You kind of flip it around, pass it in. The only problem is that it's down. That you see this later, right? So because you know the solution. So here you have it. You could put I as a parameter down here, I, and then up here you could have a parameter copy of I. And that will, I like that a lot actually. The only kind of slight problem is that you pass in I down here, so you kind of have to jump to the end to find out what's going on inside the block. So you can't read from top to bottom, you have to jump to the end and then back in order to understand that the copying happens. So it's not like one step after another.
Все, давайте поблагодарим Акселя. Время кончилось.